Hey guys, Sharky here, AP Physics 1. We're still talking about projectiles. And this is our third video. And we're going to be looking at what I call angle problems. So last time we talked about cliffs and cliff problems and some of the nuances there. These are called angle problems, and they're exactly as they sound. Something is fired at some angle, and it goes pew. Yeah. Ooh. There are a lot of applications for this. Right? So we're going to be talking about angle problems. I need to tell you about this. This is some of the lab stuff that we like to use. In fact, there is a lab that I guess you've already done that uses this, but this is a nice little program, and you can do certain things with it. I'm not saying it'll necessarily help you answer questions completely, but it's pretty cute, and you can move things up and down, and you can fire things at angles, and you can do this type of stuff. And so this is what we would refer to as our typical angle problem. Okay, I actually put this in. There we go. And so this is the picture that we're going to be drawing. Okay, so here goes nothing. So in an angle problem, we have something that is going to start over here on the ground. It's going to be launched or kicked or thrown or what have you, and then it's going to do its thing. So it looks like that. And you have this nice parabola. A couple things to note. It begins and ends on the same height. Some problems do, some problems don't. We're going to start with one that just starts on the same height. So it begins and ends on the same height. I draw a vector over here to represent the initial velocity of our projectile, whatever it is. I can make a chart. These are all things that we can do. And the chart will have two columns. Blue for x-axis, left and right stuff. Green for y-axis, up and down stuff. So here's our first problem. I'm going to give you guys these practice problems so you can fiddle with them. See how it says angles here. Right. And so usually, a lot of times, a lot of these problems refer to football. We have a player kicking a football from ground level with a certain velocity. That should be at an angle of 30 degrees above the horizontals. That's above the x-axis. And then they are asking us to solve for three things. So it looks like I have two numbers, and that's it. I have some angle, and I have an initial velocity. I'm going to put those in my picture. So here they are, put in the picture. It's kicked at some angle. I'm sure there's a force, but force doesn't come into play here. We don't care about what the force is because we only care about what happens to the ball after it leaves the foot. The velocity initial is 27. I guess I can call that V0. Now, I got to fill in my chart with stuff. Now, people are already a little antsy because they're only given two things. Okay, how do we start these problems? So the question is, this velocity here, is that an X thing or a Y thing? What do you think? Well, turns out it's neither. Because how is it being kicked? At an angle. The angle is 30. What does this mean? This means some of the velocity is in the X and some of it is in the Y. Notice I didn't draw this blue or green. So these are already more complex problems. The first thing you have to do is you have to figure out what is my speed in the X, and that goes on this side, and then what is my speed in the Y, and that goes over here. And what I usually do in class is I will take this part of my picture and I will zoom in, and I'll show you that now. All right, here's a picture blown up for you. You get a right triangle, okay? This velocity, this vector represents the speed of the ball as it leaves the person's foot, 27 meters per second, and it's at some angle, in this case 30 above the x-axis. What we have to do is figure out how much of that speed, that 27, is x, and how much of that is y as it leaves the foot. To do this, we use trig. We break it up into what are called components, if you recall. We did all that right triangle trig stuff. And so you need to figure out what is my speed in the x and my speed in the y. And it's very simple. This we call V0. This is our resultant of our right triangle. To find your speed in the x, you use cosine. You take your total speed and multiply by cosine of the angle. To find the speed in the y, you take your total speed and multiply by sine. So when we do this for the x, we get about 23.4-ish meters per second. Remember, if this vector is meters per second, then these little vectors are also going to be meters per second. And this goes in our chart where? Right here. That's where it goes in the chart. On the x side, remember, it's both. Why is it both? Well, it's both because we turn air off, right? We turn air off, there's no friction. So what happens in the x direction? In the x direction, you don't speed up, you don't slow down, your velocity is constant, which means acceleration is 0 meters per second squared. All right, and I do the same thing for the y, 27 sine 30, okay? About 13.5, and that's where this goes, right there in my chart. All right, that's the speed it leaves the ground with going up. Now, as it goes up, what happens? As it goes up, 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 it will slow down because Earth is pulling down on it. So the acceleration in the y-axis is negative 9.8 meters per second squared. Yeah? All right. Next thing I can do, I can say, well, it starts over here in the x-axis. We'll call that 0. And then the ball ends up a certain distance away. This is called range. And I can do that. On the y-axis, it starts on the ground. It goes up, 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 stops, comes back down to the ground again. So as long as it begins and ends on the same level, it's, you know, if you're assuming it's a level surface, then these two can be 0. Isn't that nice? Okay. And this is what I can do. This is all the things I can put into my chart right now. Go back and look at our problem. They want what's called hang time. So they're wanting time. Hang time. If you ever watched a football game, they usually, when they have like kickoff or a punt, they'll put a little clock in one corner and they'll time how long the ball is in the air. So that's what they want. They want the time for the ball to be in the air. So we're looking for time. So if you recall from the last video, time is the same in both columns, right? So the time it takes for the ball to go from here along the x-axis to here will be the same as the time it takes the ball to go all the way up and come back down, right? It's not like the ball is going to break into two pieces and the two pieces arrive over here at different times. They want something called hang time. So here's what you got to do, right? You've drawn your picture, you've made your chart. You have to choose a column and an equation. I'm going to show you what to do. Most of the time, you're going to find time in most of these problems. And most of the time, you're going to find time in the y column. If you look at the y column, you know more stuff. Look at the x column. You know 2 zeros and you know 2 numbers that are the same. When you try to use just this in any of your equations, you're going to hit a wall very quickly because you just don't know enough. I'm going to use the y-axis. Now, what equation should we use to find time? If you watched my other videos on projectiles, then you can probably guess which equation we're going to use. Hey, if you guessed equation number 2, you're the winner. Equation number 2 is a great one to use for time, and we can do that here. So I'm going to start plugging things in. Here we go. Here's what I get. I get this equation that says 0 equals 13.5 times time minus 4.9 t squared. 1/2 of negative 9.8 is negative 4.9. The t, this t, is the only one being squared. Now this thing, this equation right here, you math people, what type of equation is that? It's called a quadratic. Ax squared plus bx plus c equals 0. And you get a quadratic. And there's a couple ways to deal with quadratics. I'm not a math teacher, so I am not going to be doing a whole lot of math here. My assumption is you've seen quadratics before, you are in AP Physics. You're going to have to be able to deal with these things. One way to deal with these is to factor them. I'm horrible at this, and this is not something I gravitate to, but some of you are real mathy and you can do it. Just factor it. Another thing that you can do is, this is a long way, quadratic formula. You can invoke this. Now, if you do this, you got to do all your math right, and you're actually doing this twice. See how it says plus or minus here? That's because you get two answers, because quadratic equation gives you two results because you get a curve. And the curve will cross the x-axis in two places, so you actually have to do this twice. So you see this picture right here, you see how you get this big curve. It crosses the x-axis in two places, so you'd have to do that formula twice. I cheat in the sense that I have a little formula built into I typed it into my TI-83. It's called Quad. It does it for me. One thing that you can do is you can just Google a quadratic calculator. There's a gazillion of them, and you can use that. This is all up to you. So I just went to some site and I just typed it in, right? A is negative 4.9, B is 13.5, C, if there is one, in this case there's not, so it's going to be 0. This is A, negative 4.9, this is B, 13.5, your C is 0. So when you go and you type this in, you get two solutions. You'll get some positive number, and then you'll either get 0 or you'll get some negative. We're solving for time, so the one you use is the positive one. So our answer is 2.755 seconds, or thereabouts. And then I can put this in my chart. I'll go back and look at our problem for a second. So the hang time, the total time in the air, was 2.75. And I had to use quadratic equation for that. That's annoying. So that's hang time. Okay. Now, how far does the ball travel before it hits the ground is the second part. Let's see if we can figure this out. What is this? How far does the ball travel before it hits the ground? How far? That's a displacement. How far does the ball travel? That tells me it's a displacement. It isn't the x or the y. So how far does it travel before it hits the ground? They're talking about this x displacement, which is called range. That's my question mark there. I'm going to be in this blue column, the x column. I'm solving for range. I'd love some equation that just said delta x is equal to what? What equation can we use? Well, that's right, equation number 2. Good old equation number 2. Seems to work all the time. I can plug in numbers. And remember what happens. Since a and the x is 0, this all goes away. And really we're just left with this right here. My V naught was 23.4. My time is 2.7. Let me just do this real fast. And there's my range, 64.35 meters. I can put that in my chart right here. Done. Last part. What is the maximum height the ball reaches? This is a tricky question. So now we're looking for max height. Talking about height. This is a y-axis thing. Okay? So we're no longer doing blue stuff. They're asking us for height. Now this is strange because we have two zeros here. And that's because from here to here, the height doesn't change. So we're going to have to alter our chart a little bit here. Let me show you how. So in the y-axis, what this thing does is it starts on the ground at 0. And it goes up, 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 and at the very tippity top, it will stop. And that's what they want. They want that final position in the y-axis. I'm going to put a question mark right here. So this is kind of tricky. Up here at the top, it actually stops, which means at the top, which is halfway of the motion, right? We've only gone halfway. The speed at the top, when it reaches max height, is 0 for a split second. So I can actually put 0 into my chart right here. Now, this is only half of the motion, which means this time does not work. What do we need to do with this time? At the max height, it goes up and stops. That's only half the motion. So I have to take my time and divide by 2. I'm solving for a displacement. What equation can I use? Hey, if you guessed equation number 2, you're the big winner. We can use equation number 2 almost all the dang time. And so I'm going to go ahead and plug numbers in. Now remember, I'm using only half the time to find this max height because it hits max height at only half of the whole path. So I do my math in these two chunks and then subtract, and I get about 9.3 for my height.